talking not quite about how not to get a yuck factor, but we're talking about how to get soil properly. No, yeah, I think I'll better let you talk, Adam. I'm too.
Can you hear me?
Yes, and see your picture.
All right. Well, we're lucky. A thunderstorm just ran through here, but power seems to be on. So, thank you, everybody. Thanks for having me here again. So this will be an update on my research for my PhD at the University of Minnesota, where I am exploring the transformation of regolith into soils, in particular using earthworms to hopefully provide agriculturally functioning soils for an expandable human presence in space. Oops. Uh, just a little bit of background about myself. I'm a professional engineer by day. I've worked in research and development across many different industries. I really focus on test and quality, as well as project architecture and design and product management. Educational background, I have a bachelor's in economics and philosophy, a master's in software engineering, a master's in bioinformatics and computational biology, a graduate certificate in space resources, a master's in space resources, and I'm a PhD student currently. But really, what I am is an aspiring moon farmer. So I've also joined the National Space Society as a space ambassador. It's a volunteer outreach program. I found it very helpful, and so this is kind of part of that outreach. So, what are my research goals, right? And for my PhD, I have larger goals, but for my PhD, I'm trying to develop and characterize methods to transform lunar regolith into something like soil to support off-Earth agriculture. And this really has what I would consider four main areas of change. There's the biological change, there's the chemical change, there's the physical change, and the structural change. And we'll kind of work through all of those as I present here. And so I think this audience is pretty familiar, but the problem I'm trying to address here is that food is the critical gating factor in human space habitation. We've probably heard of the tyranny of the rocket equation. Well, humans are in many ways chemical rockets, and the more farther we want to go into space, the more food we need to bring, and the more food we need to bring, the more fuel we need to bring, and therefore the more fuel we need to bring, and it's a vicious cycle. So unless we're capable of living off the land, or at least augmenting it, we're really not getting anywhere. The chart on the left, that was something I calculated in a few years back. But basically, what it tells us is we, with current rockets and launch and whatever, we can maybe support 14 people on the moon. That's just because people consume about 2 kilograms of food per day. And so that 730 kilograms a year is basically one supply drop per person. But it's not just food. There's many experiments going back throughout kind of history. People need plants for medicine, for entertainment, for health, psychological support. We're co-evolved with nature. We don't do well when we're completely isolated from it. And also, like Nicholas was saying, we need to be able to sustain these operations and provide some value to Earth. And ultimately develop a cislunar economy. So my proposal on how to solve this problem is to use lunar resources and transform the regolith into soils and shorten those supply lines and do so in a regenerative way. The regenerative agriculture movement I find very inspiring. It gets away from the industrial system of chemical inputs and essentially just mining out the soil. And instead it focuses on building the soil while producing life by leveraging biology. And if we do this, I believe we can develop multiple revenue streams. I do have a small startup that's kind of in hibernation while I finish my doctorate, but I believe this is very, very possible. And this research can dovetail back to Earth and help improve situations here, right? When we look at Earth, there's many degraded environments. We can use this regenerative approach. If we can green the moon, we can green anything. We can also learn how to improve our ability to handle pollution and radiation. We can develop closed loop systems for damaged or degraded environments or entirely new places. Underground, right? If we're farming underground on the moon, there's really nothing to stop us from farming underground efficiently on Earth and restructuring our global supply chains to be more resilient in the face of natural disasters or other issues. We can potentially increase yield by developing new cultivars and new crops, and we can improve soil health just for the benefit of not all mankind, not just all mankind, but the world at large. So, with that background, how do we do this, right? And I believe that we can do this in a very accelerated way, and the research I believe backs that up. So, why do I have two pictures here? On one side we have the moon, right, and then the other side we have a lush tropical area. What's not immediately obvious, if you haven't looked into it, is that the underlying rock is the same rock. The basaltic igneous rocks that we see on the moon that dominate are the same types of rocks we tend to find in tropical areas on Earth. And so the question isn't for me if, it's how do we make this happen? And in a way that works for our timeline. So just a little background on the moon. Won't go too into it, but we have two main types. We have the highlands, it's kind of the whiter grayish part, and the mare is the darker part when we look at the moon. These are the highlands is dominated by plagioclase, feldspar, olivine, and pyroxene. The mare is much more pyroxene basalt heavy. Both of these we see on the Earth. So, for example, Hawaii and Iceland have a lot of mare lava flows, as well as plagioclase, feldspar, and other items like that. And the moon is dominated by the regolith, so this powdery, dusty substance that is largely unweathered as we would think of it on Earth, though it has experienced oscillations in temperature over time, as well as we're now starting to see some volatile flow. When we get into this mineralogy, we can see in the top box there the composition of highlands rocks. Again, it's mostly plagioclase, feldspar, some pyroxene and olivine, but a northicide by far is the dominant composition of the highlands. And then we also see the mare basalts. The mare basalts also have plagioclase, pyroxene, and olivine, but there's also the presence of ilmenite, which is a titanium heavy mineral that many in the space resources community are interested in potentially mining as a source of metal on the moon. But the mare basalts are much more pyroxene heavy, and pyroxene is kind of a black mineral, which gives it the different color than the plagioclase, which is a much lighter in color. So on the right, we can see this is a chemical weathering or a mineral weathering chart. So I've highlighted here the minerals we might see on the moon. We have olivine, pyroxene, feldspar. We also have the volcanic glasses that are formed. So these are variable, and I don't think we really know all of their compositions, but really these top categories. So we can expect olivines and pyroxene to weather potentially into amorphous hydroxide oxides or possibly down into smectites. This is speculative. We don't really understanding mineral weathering is complicated on Earth as it is. It's highly susceptible to things like humidity, seasonal temperature cycling, seasonal rains, that kind of thing. So which you could start with a rock in one part of the Earth, and it will end up in some places as a gibbsite, and other places as the kaolinite. It can vary pretty widely. One of the questions for further research I think we'll need to look into is what rocks do we want it to weather into, and how do we control conditions in a lunar soil factory to get the desired output. But it's something certainly over the last year my thinking has evolved heavily towards. Sometimes I get questions around, can we grow plants on the moon? I believe that this is possible. A couple of years ago, we had an experiment out of University of Central Florida where they germinated plants, Arabidopsis, successfully in Apollo 11, 12, and 17 samples, as well as using a simulant. You can see that here. These all grew relatively well and relatively in sync with each other. In fact, the simulants in many ways did the poorest, which I think validates simulants as a test bed. Simulants, for those who don't know, are just rock that has been specifically created in such a way to simulate the lunar samples that were brought back on the various Apollo missions. Also back in the Apollo era, they did a lot of testing around health and safety. So we can see this radish here that was exposed to the regolith, the actual regolith. No ill effects were found. It grew just fine. The Chinese program, the Chang'e 4, did carry with it a plant growth experiment. You can see down here, there's one of the cotton seeds sprouted and grew upwards, which indicates to me that some gravity is a lot more than no gravity. And we also have the moon trees, which are scattered around the world, which are seeds that went off into space and came back and continue to grow today, as do their children and further generations. So all of that lends credit. And I believe Artemis is also selected. Plant growth is one of the first experiments they'll be doing. So it's a lot there. I'm not going to read this chart too much, but basically when we compare soils to regolith, there's a lot of deficiencies in regolith compared to what we might want in soils. It starts out completely unstructured. When exposed to water, it's very prone to hard panning, and it's extremely thirsty, so water behaves in weird and kind of counterintuitive ways. It generally lacks the ability to hold ions for cation exchange capacity. So that's the ability for soils to hold on to nutrients and make them available. The nutrients are low or in their unavailable forms. There's basically no organic matter. There's no microbes or fungus on the moon that we know of, though. And the pH is in bound with what we would expect. So that gets to kind of the core of the research. So my first part of my PhD project is what we've been calling the Moonworm Project, and it's basically a characterization of the effects of earthworms on regolith simulants across those different domains that I had explained earlier. A little bit about earthworms. There's kind of three main types. The epigic, probably the ones we most commonly think of. They live in the leaf litter. We also have anisic. Those are very large worms that burrow vertically up and down into the soil. And then we have endogic worms. Endogic worms live exclusively within the soil, and in some cases they even feed off the rock. We have been doing work mostly with epigic worms, in particular red wigglers or Asenia fetida. This is primarily because they're the most commercially available worms, and they're very hardy and relatively easy to keep alive. This is kind of old news compared to last year, but in general, found a way to match the amount of manure to mix with the soils. These levels need to be monitored very carefully in my experience. You have to have the right amount of water. You have to let the water kind of soak in. Dry regolith is potentially deadly and certainly appears painful to worms. They breathe through their skin, and it will suck the moisture right out of their skin. So a lot of trial and error took place to kind of crack the code in terms of ratio. In terms of manure, I've been using horse manure as an analog for human manure. Horses are monogastric, just like humans are. It's readily available and does not require a lot of paperwork. So that's what we're doing. I've had success with night crawlers in the past. These are very difficult to grow, even terrestrially. People have tried and failed. But we can see that these powerful night crawlers are able to break up the hard pandish regolith manure mixture and even begin to do burrowing. This is an example of the Highlands material. So we can see this is 4 worms in a 200-gram dish. We can see the Highlands manure regolith mixture, and we can see the casting starting to form by about day 4 or 5. The worms are able to infiltrate the media. It's dried out. Some cracks have formed. The worms then begin to exploit it. By day 18, they've worked over the material quite heavily, and by day 28, you wouldn't know that was moon dust if I hadn't told you. So they really work it over very well. This is the mare. This is the mixture when it's dry, and when you add water, you can see that it binds up to itself very, very quickly. The worms are unable to enter it, but a few days more pass, and the worms are able to start infiltrating the media. You can see these paper towels. This is to simulate the leaf litter. The survivability greatly increases if the worms have a place they can retreat to, and particularly those first few days, it allows them to have a refuge. By day 30, they've worked it all over. By day 45, it starts to smell of soil, right? That after rain kind of soil smell. It becomes very, very obvious. By days around 60, we actually see a color shift. This isn't just a function of lighting. It becomes that much darker black, richer color we would associate with topsoil. And by this point, there's none of this has not been turned over by the worms. So very, very successful. Have seen both in both types of mixtures babies, so that suggests that there's long-term sustainability as they're capable of reproducing. And I see my time is starting to drift down. This is what this stuff looks like under electron microscope. So the highlands, we can see these very sharp, jagged structures. Mare as well, a little different composition. And that's what a healthy, kind of normal earthworm casting would look like here on Earth. So we took pictures of the castings, right? So after one day, the mare, we are seeing castings. We are seeing the minerals starting to get into the worm's guts and being processed over. By day 2, we're starting to see organic matter being incorporated into the castings. By day 3, we can start seeing very incorporated bodies, right? So here we have what looks like organic matter being bound up. We also start to see here, this is somewhat subjective, but we can see rounding to the particle grain. This is indicative of the worm's gizzards. They have a gizzard that will grind rocks and other matter inside them. And Suzuki et al., a laboratory out of Japan, had found that they did quite significant changes to the particle geometry and physical shape. We're seeing that here in our imaging. After a week, we can see they've developed kind of a normal adjustive cycle. I don't think I mentioned it, but the worms were purged. They were left without food for 48 hours so that no contaminants were entered into this. So this is all just regolith and organic matter. We can see the organic matter becoming integrated very, very heavily. These are much larger sticks and pieces into them. We used spectroscopy to confirm that this thing that looked like a stick was in fact a stick, and the other areas were present in terms of the silicon oxides and other things we would expect from lunar regolith grains. So that's just a way to validate that what we were seeing was what we saw. And by day 30, the mixture's been very heavily mixed over. You can see here there's some artifacting in this imaging. But you can see quite a bit of particle groundness that we did not see in that original image, indicative of that heavy weathering physically that we were expecting. We got pH results. Can't remember if I had this last year, but we find that pH is trending towards 7, fairly slow. This is consistent with the literature. Worm castings are pH neutral. But it will take a while for things to kind of dilute and become processed. And we can see that the dishes with the worms in general are trending more heavily towards that 7. So highlands are mildly acidic at 6.5 or something like that. And then you add the manure, but with the worms, it moves more towards 7. And then the basalts are a bit more basic. And we can see that over time, it's just a little bit down, but it's nothing particularly pronounced. Just more of a trend. Perhaps the most compelling of our results are the soil testing results. So there's a lot of numbers here. You don't need to read them all. But basically, we've compared total carbon, total nitrogen, and cation exchange capacity between the worm dishes and the non-worm control dishes. And what we found was that with the worms, there was a slight reduction in nitrogen in the beginning, but improved overall. There was a significant increase in carbon and the ability to hold on and retain it. And then perhaps most compelling is that we saw a 25% increase in cation exchange capacity, with some dishes even being significantly more higher than that. So all of this says that in the highlands with the manure, we're seeing generally an improvement or a sustainment of the ability to control nitrogen and hold it in. We're seeing a significant increase in the ability for carbon. So that's that organic matter being worked in through the worm's gizzards into the castings and being held onto. And then the cation exchange capacity and going up significantly is the creation of pore spaces, mineral weathering, hydration. There's lots of potential reasons why this is happening, but significantly improving the ability to hold on to those nutrients. Mare, we saw similar results. Nitrogen kind of improved as well. It improved carbon, but it was not as pronounced as in the Mare, or as in the highlands. Sorry. And we also saw again that about 25% improvement in cation exchange capacity, which suggests that the earthworms really quickly improve and structure the soil in a way that's beneficial. Some of the results I'm still working through. We've done extractable iron testing. I'm still working through this. We had thought that the worms would kind of weather the iron. Initial looks at the data weren't so obvious, but we're still working through this along with these other types of elements. We have collected the spectroscopic data. Carpenter et al. Is another paper. They found that a northite will begin to chemically weather within 2 months. We are seeing in this, just a quick analysis, some indication that the spectral signature is changing. The olivine is also very present. They found that was much more resistant to weathering. So it'll be interesting to see the comparisons between the Mare and the highlands. But we have seen some preliminary stuff. And for those who haven't seen these are spectroscopic curves, and kind of where the peaks are offset are indicative of some chemical structural change, right? So these got these two lines. The top one is without worms, and you can see some of these peaks are offset. So that's kind of how that analysis works. We very recently got the bioinformatic data, so we're going to be doing analysis, bioinformatic analysis. This is not from my research. This is from Zhu et al. On their bioinformatic approaches to reveal metagenomic characterization of soil microbial community. But I show it here because it will be very interesting to see how our bacteria and microbiome presence compares to various earth biomes, as that might give us an indication of what species or at least microbes could potentially be happy, of course, notwithstanding lunar conditions and gravity and all that. We did some plant growth trials this spring. I think this is extremely promising. So we've been focusing on dandelions. I think they're a very useful plant. And we can see here on the right, this is the dish with the worms in it. This is the dish that was just raw simulant, and this was a kind of organic potting soil, more of a compost. And I can say without a doubt, the dish with the worms did better than all the other dishes combined, which is a major testament for the ability. Many of the dishes suffered water infiltration issues, or the roots became very stunted as they attempted to move through the material, or they showed signs of leaf stress, indicating some nutrients were not available, even if they were present in the manure dishes. But we can see very, very well developed root structure, a very healthy color of the leaves, all of which indicate that dandelions are a potentially good pioneer crop, as well as validating the moonworm hypothesis as a whole. These are the root tips of those same plants, and you can see this is a very healthy looking dandelion root tip. It's well rounded. It's engaging with the minerals and creating an interface between the biology and the minerals. If we look at just the raw simulant, this root is very stunted. It's much more flat. You can see it's trying to push its way through the minerals, and it's giving it a good shot, but it's really struggling. And in case of the pure potting soil, it's just not really interfacing with any minerals. There's nothing really there, and it seems stressed for it. Dandelions being a pioneer species, they may want that minerals, not just a compost. So yeah, as kind of wrapping up here for time, we're going to continue to finish the characterization experiments, do our analysis, and then we're planning to do more plant growth trials this fall. And then longer term, we can look at things like human compost, orbital validation, that kind of thing. There is some intellectual property pending around this, just as a disclaimer. Here's the research team. We've got my committee members, advisors, professors Yang, Yu, Ishii, and Bailey, as well as Tristina Ting, undergraduate researcher, and Tyler Baum, who was a master's student and served as a technician. I'd also like to acknowledge the University of Minnesota, the Undergraduate Research Office, the Genomics Center, the ASOS Lab, the Minnesota Space Grant, and the Office of Graduate Fellowships and Awards, all of which have provided funding to support this work. So with that, I've got about 5 minutes and say thank you, and I'm happy to take any questions.
And we have several questions from the in the chat here. The first one is, what about other organisms such as fungi, bacteria, nematodes, and so on?
Yeah, so I mean, that's a great question. One of the key things in a research is to kind of focus, but we have seen mushrooms sprout. They're volunteers, so certainly some fungi are potentially available. The bacteria, as far as I know, there's no bioinformatics study ever done. Ours is one of the first, certainly pre-publication, but it should give a good baseline. Nematodes and other organisms, I think, are all very valuable as well. So. But right now, just focusing on the earthworms.
Yep. Yeah. Seems like a good place to start. Same. Also from Jason. I'm very interested in spreading life across the solar system. I would rather bring living things along with me rather than do it all mechanically or upload my mind to Computronium. That's not a question. It's more a compliment for doing the right type of work, I think.
Yeah, thank you. I think biology is really it's often underappreciated, and it's a self-replicating machine. So why don't people try to invent self-replicating robots, but we have this stuff already. So
and well tested and tried out, and I have been working for millennia.
Yep.
I have a couple of questions actually. How much manure do you need to create a kilogram of soil from regolith?
Yeah, so Caporale et al., which is a lab out of Italy, they were doing a 70-30 ratio, 70% regolith and 30% manure by mass. So that's where we've been focusing, because they found that to be ultimately best for plants. So that's what we've been using.
Yeah. Could you reuse that soil once the worms have been through it, or do you need to add more manure to keep things going?
We haven't conducted kind of succession planting, but my instinct is that we could reuse it and continue to keep building the soil. So you may compost onto the top or something like that, but in general, right, a healthy garden bed, if managed well, stays healthy.
Yep. From Frida Taube, would the system eventually have somebody who eats earthworms? I guess that's.
I mean, I'm not super interested in eating earthworms myself, but we could feed like space chickens or something like that. Different ways to kind of flow through. The earthworms are there more to structure and alter and create the soil.
Yeah. And Chris is saying, great research. Have you looked at doing some mechanical pre-processing of the regolith before turning it over to the worms to speed up the whole process?
Yeah, actually we have. We've done some looking at mechanical systems to change it. It ended up creating kind of an explosion of variables, but we have done some pilot work. I don't know how quickly it's going to speed it up. It seems about 30 to 60 days is what we need to create the soil. So, if we cut 5 days off of it, but I think it's worth exploring. I just don't know. We don't have the data to compare.
Yeah. Yeah. Gary Barnard.
Yeah, Adam, very interesting presentation as always. Question though, one of the things that was discovered with respect to space station is human beings, of course, really do travel with their own biome. And if you go through and disrupt that, as they did by irradiating the food at first, it causes fairly serious problems. Have you looked at the notion of comparing the resulting, biome that could be created with your worm environment, with what's going to be appropriate for supporting a human, in such a biome cycle?
Yeah, it's a great question. We've had some discussion around it. It's too early to kind of say. We're still working through that. One thing I will say is that earthworms, if you feed them human waste, they are basically known to sterilize all pathogens. And so one of the things that we see on this International Space Station and Mir and these other places where you get essentially bacterial seeding from human activity around the space station, and because there's no other microbes to compete with them, those potentially pathogenic microbes have taken over, or there's like famous instances where they ate through the wires and things like that. So my personal inclination is that by having healthy microbes around us, such as those from soil, that would actually increase health. That's speculation on my part, but there's some validation on Earth, right? So there's a lot of studies coming out now that like children who play in the dirt end up being healthier because they're exposed to all these different microbes. So that's my gut, but we would still need a lot more data on that.
I think that's a good final remark on that. And we have had the egg timer